Most of you know that one of the major ways that we transport energy is through electricity. And we've talked about a huge number of sources of electricity so far this year. We've seen that the kinetic energy of air molecules, the wind, can be captured by a windmill to make electricity. We've seen that the gravitational potential energy of water molecules that have been moved up high by the sun can be captured by a hydroelectric dam and used to make electricity. We've seen that burning coal or natural gas or even a biofuel like wood can be turned into electricity. We've seen that the heat of the earth, geothermal energy, can be turned into electricity. And we've even seen that energy stored in matter itself, an exploding atom, can be captured by a nuclear power plant and turned into electricity. And that seems like a huge diversity of sources to make the same thing, electricity. And what's interesting is that most of these energy sources are turned into electricity the same way. It's through something that was discovered in the early 1800s by two guys named Michael Faraday and Joseph Henry. I've got a coil of wire here, and it's hooked up to what's called a galvanometer, which just measures the flow of electric charge, which is known as electric current. You can basically see that this is the way we're going to show that electricity is being made. The galvanometer is hooked up to the coil of wire, and I'm going to take this magnet, and I'm going to plunge it in and out of the coil. As you could see when I stuck it in there, current existed as it was moving in, but then it stopped. If I pull it back out, I get more current, but in the opposite direction. So apparently what this coil of wire and this magnet are doing is they're converting the kinetic energy of my moving arm into moving electrons or electricity. And this is the way that we actually use all those energy sources to make electricity. We make a magnet move near a coil of wire, or vice versa, and that makes charges move. It makes electricity. Now, doing this all day is not an efficient source of electricity, so a better design was come up with. And here's a good model for how that works. I've still got a magnet. The magnet is the horseshoe-shaped thing with the tan wire wrapped around the bottom. The coil of wire is now the thing that moves. It's these two coils of wire wrapped around that disc, and they actually spin inside the magnet. I've also got this hooked up to a galvanometer, and watch what happens as I keep spinning. We see that same changing direction of the electric current. We'll look much more at why this current seems to alternate and change direction when we talk about the physics of electricity and magnetism. We'll look much more in depth at this. But the bottom line is, I'm making electricity by turning this crank. And if you replaced my muscles with one of those other energy sources, that's how you turn them into electricity. It's pretty easy to see how a windmill works. Instead of my hand here, you have a wind turbine that can capture the moving air, and the air spins it. In a hydroelectric plant, it's equally easy. You have a water wheel, or a turbine, and as the water falls, it turns the turbine, turns the coil, makes electricity. In a nuclear plant, or a fossil fuel plant, or a geothermal plant, there's an intermediate step. You use that energy source to heat water. And then that water, either as steam or high pressure water, it turns a water wheel and makes the electricity. But that's how all these different energy sources we've talked about all can become electricity. You move a magnet near a coil of wire or vice versa, and that causes charges to move.